say this one more time because it's important that you realize that we are learning a process to analyze functions, and we're kind of at like the first step. The first step is to find extrema. Extrema are max and mins. But there's like more to this process, and we're going to learn it in the next couple sections. So eventually you kind of put this all together and you're going to say, now I see. Now I see how it all connects. But right now we're just finding extrema, and I want to show you how we can find the extrema of a piecewise function. Okay, now remember, behind every one of these problems is a graph. But you got to be careful that you don't just like look at the graph. It's almost like you have to have some discipline and say, I'm going to do the calculus, because it'll pay off, because eventually you'll put this all together. Okay, so we're actually not going to graph this. That's typically what you do with a piecewise function in almost like any math class. It's like, okay, make a graph. But what I want to do is I want to take you through the same steps. It's called the critical points or the endpoints. Now, we don't have any endpoints because we don't have like an interval. But what we do have is a parabola for numbers less than 1, and then we have like a linear line for numbers greater than 1. Okay, but again, there's no endpoints. So what I can do is I can jump right in here and I can do the derivative, because of course that's the critical point. Now, can you do the derivative of a piecewise function? Yeah, it's something that we did in a small lesson one day. You just do the derivative of each piece. So I'll be careful this time. We get the derivative of the parabola to be 2x minus 4. You still want to keep the interval there, okay? Because that derivative only applies for numbers that are less than or equal to 1. And then it looks like the derivative of the other piece is just the number 1. And that's for numbers greater than 1. Now, according to the critical point method, you take your derivative and you set it equal to 0. So let's take 2x minus 4 and set it equal to 0. Seems like kind of like what we've been doing lately. And it's not hard to see that x equals 2. But here's where you want to be a little bit more like introspective. You want to be a little bit more like see what's going on here. And what's going on here is that this derivative only works for numbers that are less than 1. Ooh, that means that it's not going to work for a number that's outside of that domain. So what that means is that even though x equals 2 is what solves this, it turns out to not be part of my critical point sort of list. It's not part of my list. Okay, no big deal. We didn't make a mistake. Take your other derivative and set it equal to 1. Now, sometimes this can be a little strange because, well, it's like saying that 1 is supposed to equal 0. Okay, now, it doesn't say that 1x is supposed to equal 0. It says 1 is supposed to equal 0. Same thing, kind of be a little thoughtful here. What does that mean? What does that mean? That means that it doesn't happen. That means that you don't get a critical point. Now, so far, what's kind of happened here is a big fat nothing. We don't have any critical points. We don't have like that magic x value, okay, because both of these have been thrown out. Remember that other idea where it's supposed to equal undefined? Let's talk about that. Let's talk about equaling undefined. It's kind of we have to be careful how we say equals undefined, but the truth is that we're trying to figure out when the derivative is undefined. When is a derivative undefined? Well, yes, when you get a 0 in a denominator, but also when you have a slope problem. Now, you would have learned this in the last chapter, but it was kind of a small idea. But there's a slope problem when you think about the slope on the left and the slope on the right. Let's talk about that a little bit. Let's talk about the slope on the left. Because the slope on the left, I can spell, the slope on the left is going to happen when you investigate the x value for that derivative. When you investigate the x value of 1, for that derivative, you find out that you end up with a slope of -2. Now, here's where, if you're like, whoa, I just missed what you did there, you have to understand that I am taking the transition point and I am checking to see what is happening on the left. That's this derivative. And then in a second, what's happening on the right. Okay, that's because at a transition point, you have the potential for a problem. How about the slope on the right? The slope on the right is always the number 1. Okay, it's always the number 1. Slope on the left was -2. And we have a technical problem. Listen, this is kind of like a technical thing today, but it's important. There's a technical problem, and that is simply that those two slopes are not the same. You've said it before. You said the slope on the left does not equal the slope on the right. And when the slope on the left does not equal the slope on the right, the derivative is undefined. When the slope on the left is different than the slope on the right, the derivative is undefined. It's a technical idea. So what does this mean? Well, this means our transition point. Now, you got to get the idea here that x equals 1 is the transition point, just because that's the way this was set up. But that means that x equals 1 is a critical point. And just in case you forgot, that's what we're trying to find. We're trying to find critical points. We just found it through some technicality. So x equals 1 kind of makes the list. Well, it's the only number in the list, but it needs a y value. That's supposed to be a ordered pair there. So it needs a y value. Just plug 1 back into your original equation. Be careful, plug it back into the original equation. You get 1 minus 4 plus 5. 1 minus 4 plus 5. 2, right? Yeah, 2. Now, here's the part of the lesson. It'll be the last time I have to say it, because next time I'll have taught you this next idea. But here's the part of the lesson where it's like we need to almost cheat to figure out if this is a max or min. What do you mean cheat? Well, we actually need to think about the graph. I know I said we weren't going to graph it, but it turns out to know if that's a max or min, since I don't have anything to compare it with, I need to think about a parabola. Now, I'm going to just kind of sketch this quickly. So you get a parabola, and then I have to think about a straight line. And again, I'm going to sketch this kind of quickly. But basically, when you have a parabola that intersects a straight line, that's a minimum. This point right here is a minimum. Before you say it, I'll beat you to it. This definitely was the long way to get to the answer, but it uses calculus. It uses the idea that the slopes are different. And since the slopes are different, we learned this, it was a couple sections ago, this is a corner point. And since that's a corner point, it's also a critical point. And it turns out to be that critical point that makes a minimum. Okay? I want you to see that. And I'm excited to show you like the next piece of this idea. Again, you just have to come back for the next lesson.
So if it doesn't ask you to give them like an absolute max or relative max, can you only say max?
Yes. Again, unless it says be specific, use the words absolute and relative, you may just say generically max and min. And when you open up your assignment, you'll see the first couple questions ask you to do that. And then like I've done with most of the examples, once you get to the examples, you can just say max or min.